Okay, so welcome back, everyone. So in this lecture, actually, we will focus on PBW theorem, and then I will actually outline the idea to prove this theorem. We will also actually see some consequences of this theorem. So what I will do now, like there are two versions that you can actually state the theorem. Both are equivalent, so that you can see immediately. And then what we will do, like we will focus on one of the version and then try to prove. Okay, so there are two approaches. Like I said, both versions has its merit. Okay, so the ideas that you use, okay, to prove version 2 that I'm going to talk about, so where I established this basis, so that idea actually, like we follow closely what is done in Roger Carter book. And there is another proof that you can see in Humphreys. So that is again, so that also kind of important ideas. So maybe I will outline what is happening in Humphreys proof. Maybe that those ideas will be used later when you actually go ahead with representation theory. So, okay, let me first begin with stating the PBW theorem, and then we will move on. So before that, let me actually uh, kind of fix some notations or recall some notation that we actually used in the last lecture. So we start with G being Lie algebra over complex numbers. Let's actually consider much generality because the theorem is true, the proof doesn't change at all. So you take G, so which is Lie algebra over complex numbers, and we allow it to have any dimension. Okay, so we don't really restrict anything. What we do, like we fix a basis. Okay, so let us fix a basis xi, I in I. So this is the basis of G. So the only demand that we put actually I is totally ordered. So the axiom of choice tells that any set can be well ordered, but here total order is good enough for us. Okay. So we take that I to be totally ordered set. So the ordering, I will denote it by less than or equal to. Okay, this is the order that is on their capital F. So now with this, we will work with this G with this basis. So recall, so how we constructed this universal mapping algebra. So we started with this tensor algebra, which is TG, which is direct sum of all these uh, k-fold tensors where k greater than equal to 0. So this tk of G is nothing but just k-fold tensor of G over C. So then you took this, I guess I denoted by J. This J is just a two-sided ideal generated by this x tensor y minus y tensor x minus the bracket xy. So for all xy in G. So because we wanted to have the product xy minus yx, okay, the commutator of that, okay, xy minus yx should be equal to bracket xy. So we take this two-sided ideal generated by this, and then you go modulo that. So then you get the universal mapping algebra. So TG modulo this J is your UG. So now we immediately realized because TG being graded algebra, so there is natural filtration on this TG. So that filtration induces filtration on this UG. So what is the filtration? So we defined uh, TMG. So that to be, so you take first M direct sum of all these graded spaces. So this is TKG k varying from 0 to n. Okay, so then this TMG is actually giving you filtration for this TG. So then if you take this filtration and then take the image of that filtration under the quotient map from TG to UG, you get filtration for UG. Okay, so that is something we use. So recall this UMG is the image. I guess the quotient map I denoted by pi. So this is pi of TMG. Okay, so you have a map pi from TG to this UG. Okay, so what I would recommend, because this app is not allowing me to actually enlarge the space. Okay, just like changing the slide is going to create like problem for you. You take just a picture of this and then keep it with you, like that will help you to just go back and see. So that's the only thing like right now can be done. Okay, so these notations that we are going to use. So now, so with this, you have this UMG, which is defined to be pi of TMG, where pi is a map from TG to UG. Okay, so this actually gives filtration. So this gives filtration for this UG. So then we constructed this the graded algebra associated with this UG. So where the graded spaces, okay, this is the, let's call it this gradient of UG. So this is by definition, okay, the gradient of UG is you take UMG and then go modulo UN minus 1G. Okay. So by convention, you take U minus 1G to be 0. So then we realized that there is this natural map, okay, that you have here from pi TG to UG, okay. So you have this natural map that we define omega. So that is actually gives us map from the symmetric algebra to the grade UG. Okay. So that actually comes from the natural map that you define from TG to grade UG. Okay, so one version of PBW theorem. So here is the version 1. So PB.
What is GRM UG?
GRM UG I have defined here. Na?
Yeah, okay.
Just I'm just denoting the mth graded space to be that grade MUG. That's all. Okay, so here is the first version of PBW theorem. Okay, the version 1. Let's call it V1. So that says that this map omega is an isomorphism. So this map omega from SG to the grade UG is an isomorphism. Okay, so it's easy to state once you have built all the necessary language. So in particularly, you have a standard basis on S of G. And then if you take image of that inside the grade UG, then you will get a basis there. And then that basis, okay, going to give you basis for UG because as C vector space, UG and grade UG, they are isomorphic. So in particularly, the version 2 that we can actually record as follows. So if you take Venkatesh theorem version 2, so the standard basis that you have from SG will induce standard basis here in the UG. So which is, we call it PBW basis. Okay. So the basis is written as follows. So let's fix some notation. So you have this natural quotient map. So now I'm working only with UG, okay, not in the grade UG. So pi is the map from PG to UG. So under this map, let's say xi map to small ya. Okay, just distinguish the images. I'm just writing it as small yi. So then with this notation, what we have, so you have this basis. So xi I in I. So this is a basis of G. Okay. So now what are we going to do? Like we are going to take the images of these letters xi inside UG, and then we are going to produce basis for UG. So from this, you can actually get the basis. So because I is totally ordered, what we will do, we just consider all increasing monomials. Okay. So you take x I1, R1, etc. x ik power rk. So these letters. So where all this I1, etc. ik comes from this capital I. So the only thing that you assume, because all these RIs, they are all exponents, you can just assume to be, you collect those uh, letters that are appearing here. So you can assume that all RIs are all greater than 0. Okay. So then you take this I1 less than etc. less than ik. And you also allow k to be non-negative. So whenever k 0, it's just an empty product. So you take it to be 1. Okay. So this k is also very like written off with each. So what the second version of BPW theorem asserts that, so this is the basis for UG. Okay. So basically you take basis of SG and then you come to grade UG, and then from grade UG, because that is isomorphic to UG, you come here. That's all. So this line of argument actually tells you that the version 1 implies version 2. Okay. So I will leave it as exercise. So the exercise actually like involves only this much. You have to prove that grade UG is isomorphic to UG. If you prove that, then omega being isomorphism and then taking the images of the basis of S of G under omega will give you basis inside grade UG. And then if you just trace the map from grade UG to UG, it's a natural C-linear isomorphism, then you will be getting this basis. Okay. So version 1, sorry. So the version 1 implies version 2. And converse is obvious because, as I said, so you want this to be isomorphism in this version 2. But it's already a surjective map. From TG to grade UG, you already have a surjective map. So this omega is indeed a surjective map. There is no issue. So only thing you need to prove is it is injective. So if the basis is map to basis, then it must be injective. There is no other option. Okay. So that actually tells you that converse is obvious. So you have this equivalence between version 1 and version 2. Okay.
Sorry. Is the index set I be finite?
Not necessarily. So I could be anything actually. Only thing is you take some total order on that, so that you can talk about increase in sequence.
Okay, so I don't have to be finite, but should have order, right?
You don't have?
I mean, I could be infinite.
Yeah, I could be infinite. Yeah, I could be like even uncountable also. Like you can take it to anything.
Okay.
But for all practical purposes, at least in this course, we will be only saying finite dimensional spaces. So mostly like interestingly, algebras are maximum countable dimensional. Okay. So countably infinite dimension and finite dimension spaces only you will see like in most of the theories like Cosmody algebras, Botz's Cosmody, even some other algebras that naturally come up in mathematical physics. All of them are actually at most countable dimension.
So is it right for uncountable dimension?
Then what?
Uncountable dimension.
Yeah, you can have like there is no issue because this only total order you just use and then you will be only considering the finite monomials.
Okay. Thank you.
Yeah. Okay, so let's actually first to see some consequences of this theorem, and then later we will focus on version 2 and then try to prove that actually. So now like there is no big difference between version 1 and 2, but the ideas that you see in Carter and Humphreys, they differ little bit. Okay, so I will actually tell you like when I introduce that proof of Carter. So first thing to note is, so you have this natural map from G to UG, okay, that iota. So that is indeed injective map. Okay, so you have this map from G to TG and then TG to UG. Okay, this is the quotient map, and this is this iota that you have from inclusion from G to TG. So this is inclusion, but this is surjection. So there is no guarantee that the composition, which again we denoted by iota, that is injective. Okay, but the corollary actually says, okay, first corollary of that theorem that asserts that this map is indeed injective. Okay, so that is something obvious because if you look at the image of this basis, okay, so you have this xi, I in I. So this is, it is indeed a basis of G. Then if you take the image of this, okay, the image of this xi, I in I, so that is going to be just a small xi, I in I, okay. And note that it is just part of this monomial basis, okay, because you are allowing uh, all possible monomials. No? So you are allowing all possible monomials. You take k to be 1 and then you will be just having I in I. Okay. When k equal to 1, you run over xi, I in I. And this is contained in figure. Okay. So that because of that, this entire set is basis. So this also must be linearly independent inside your, so this must be linearly independent inside your image. That means the image iota of G must be isomorphic to G. So there is no problem. And I already mentioned that this iota is it's actually algebra, like Lie algebra homomorphism. So now iota actually is an injective map. So you can identify G with IG. There is no issue. So that is what PBW theorem actually asserts. Okay. So this actually tells you that you can identify. You can identify G with iota of G. So that is what mostly people do when they get into representation. They stop mentioning different. They stop actually using different notation for elements of G and its image. Okay, they just use just the same notation. Okay, so here is another important corollary, like so which is actually used very much in the representation theory. So if you can decompose, okay, G into some sum of subalgebras, so not necessarily as Lie subalgebra, just as a vector space. Okay, so you take G and then you take G1 direct sum G2. Okay, so you just assume that both G1, G2 are subalgebras, but the sum is actually just a vector space sum. Okay, for example, you must have seen such decomposition for semi-simple algebras. So let's keep one example here. So if we take G to be SLN, okay, so we can talk about the diagonal matrices inside G, okay, so which is a subalgebra, which is indeed abelian subalgebra. So then you have this n plus, which is upper triangular, okay, strictly upper triangular. And similarly, n minus, which is strictly lower triangular. Okay. So then if you take such subspaces, they are all subalgebras. Okay. All of them are subalgebras. You can write G as n minus, direct sum h, direct sum n plus. Okay. So you can actually permute it, not a problem, but this particular way of writing is important for representation theory. So that is why we write it n minus first, h, and then n plus, because we are going to develop highest weight theory. We use there. And this is what you call triangular decomposition of G. Okay, so this is called triangular decomposition. Now note that. So this is not direct sum of subalgebras. This is just as vector space, you have this decomposition. Okay, this is just as vector space. So then such thing is there. Okay, this is a vector space. So then what you can tell about this UG, okay, so you can actually talk about a copy of, okay, so let's say here G1, G2 are subalgebras, and G is vector space direct sum of G1 and G2. Okay, then what we want to say, so there is this natural embedding of UG1 inside UG, and then similarly UG2 is embedded in UG2. So, but using this, you can say that UG is indeed product of UG1 and UG. Okay, so this is actually a consequence of PBW theorem. Okay, so let's explain what is the meaning of this. Okay, so let's first prove this. Okay, so for any subalgebra, you have this embedding of UG1 inside UG. So that actually tells that any subalgebras, so the corresponding universal unified algebra can be embedded inside given Lie algebra. So then we take copies of that and then take possible products and then their sum. Okay, so this is just taking possible products between elements of that and then taking a linear combination of that, and that is going to be your UG. Okay, so let's first prove this. Whenever H is subalgebra, okay, Lie subalgebra, then UH is naturally embedded inside. Okay, indeed, what you can prove slightly stronger than this. So let me make it very precise. You start with the basis of H. Okay, so let's start with basis of H. So let's call it some HI in let's say J. So what you can do, you can actually again you take it to be ordered basis. You have total ordering on J. Okay, so this is ordered basis. That means J has total order. So now what you do, you extend this basis to a G. Okay, extend this basis to G. So then you will get basis, so which you let's call it HI in J, and then union some XI in K. Okay, so this is actually basis of G. So now you want to define this algebra morphism. Okay, so using the inclusion of H inside G and then a G inside UG. Okay, that actually naturally gives you map from UH to UG. And then we will take the image of this UH, okay, and then see like what is this UG as module over that image. So let's go slowly. So you have this natural embedding of algebras. Okay. So now if you think about it, UG being unital associative algebra and UH being this okay, universal and Olympic algebra of this. So there is a natural extension of this map. Okay, whatever map that you have, the composition. So there is this extension. So let's call this is theta. So there is this unique theta tilde. Okay, such that this diagram comes. So you have a map theta tilde from UH to UG. So now what you can do, so if you use PBW theorem, so you can actually see that using this basis, you can actually get PBW type basis. Okay. So you take this total order on J and then you can extend that to total order on K. Okay. Then you can make this J union K, which is, you can call it I as total ordered set. Okay. And this order actually, when you restrict to J, it is same order that you begin with. So now using this, you can actually have a PBW type basis for G. And using that basis, you can easily see that this theta tilde must be injective. Okay, this is indeed injective. Why? Because look at the image, okay, where this HI goes, okay. So there is no difference because if you trace the image, so here you are taking HI and then the same HI you will be using here, okay, because the same image. And then as I told, this map is already like you can identify G inside UG. So the same HI will be element of UG. So now if you come here, in some sense, the same HI is here. Okay, maybe if you want to use all the notations, not a problem. Maybe let's go slow. Okay, let's call it this is iota H, then this is iota H of HI. Maybe let's call it this HI tilde. Okay. So then what happens, like if you look at the image of HI tilde inside UG, then this must be this HI. There is no other option. So theta tilde of HI tilde is going to be just HI or iota of HI. If you call this map iota. Okay. So this generator HI tilde, which is in UG, map to iota of H inside UG. And this PBW basis actually tells, okay, the monomials in that must be linearly independent, because the monomials in HI will be part of the PBW basis of this monomials of this UG. Okay, so monomials, so this strictly increasing monomial. In HI, okay, I and J are part of PBW basis of G. Okay, so because it is just part of the basis, it must be linearly independent. So the image of the basis of UH is linearly independent inside UG. So that tells you that this map must be injective. Okay, if there is some relation, okay, if there is something in the kernel, you just look at its image there. So that must be linearly independent set which is having some linear relation. So that will force that all the coefficients are zero. So that tells you that this map is indeed injective map. So since this is again like almost same map that you are actually getting, which is natural map. So and since it is injective, you can identify the image of elements of H inside UH and UG as same. There is no issue because this HI tilde map to HI, I can keep repeating, okay, this, I can just use the same HI uh, to use elements of UH as well as UG. There is no issue. Okay. So with that, what we have now, you can see that. So you have this embedding of UH inside UG. So you identify image of UH with UH. So that means I can think this UH sitting inside UG. So then you can ask, okay, there are two algebras given to you, okay. UG is C algebra, associative algebra, and then UH is also associative algebra. Then you can ask, so there is this natural action of UH on UG via left multiplication. So UH acts via left multiplication on UG. So then the question is, so what is this module? And you can say that this module is indeed a free module, okay, over this UH. That just follows from this PBW theorem. So let me just write down. So you have this injection, and this induces injection from this. Now it's clear that you have the PBW type basis that comes from this HI and then HJ, where I is from J and then J is from K. So this is basis of G, and this gives you PBW type basis for UG. So now if you think about it, you can take monomials only coming from exercise. Okay. So then that will be basis as UH. That will be UH basis. Okay. So it's not very hard to prove. So this is a very simple exercise. Okay. So if you take this xi1 power r1, etc., in power rn, okay. So where this r1, ri's are all written equal to 0. So maybe we'll take it to be positive, and then it's I1, etc. is IN. So this is coming from your K, okay, and then I1 less than etc. less than IN. So all strictly increasing monomials that are formed using this variables xi's. Okay, where xi I comes from k. Only those things we are considering. So this set, if you take, so this is indeed UH basis of UG. So that means UG is a free module with this basis, okay, over UH. So you can directly check this because this is follows from this PBW basis of UG. Okay, if you write down the meaning of this, what is the meaning of UH basis as a module? Okay, you want to have UG as free module over UH with this basis. That means if you have relation over UH among these elements, then you should be able to get contradiction. And you can easily say that if you have such relation, that will actually give you relation among PBW basis of UG. Okay, so that actually gives you contradiction. So that actually tells you that. So this is indeed a basis of UG. So that means you can treat UG as a free module over UH. Now, given this image, you can see that if you start with another Lie algebra, okay, which is a complement of this G1 or H, okay. So let's use this role notation that we have written. So if in case G is G1 direct sum G2 as a vector space, okay. So then you have this UG1 sitting inside UG and then UG2 sitting inside UG. So then you can combine them like together and then take the product of all the elements and then linear combination of that. So that is going to be your full UG. So this is just a statement of PBW theorem because you can start with the basis of G1.
Sir,
Okay.
sorry, sir. There is a question in the chat that UH basis of UG means that we are taking scalars from UH.
The basis of
The basis of UG, that is UH basis of UG, means that we are taking scalars from UH.
Yeah, exactly.
Okay.
So okay, so yeah. So if you have, for example, this setting, A is sitting inside B. So both of them are let's say algebras, okay, C algebras. So now we are thinking A as B module, okay, and you say that A has some spanning set over B, then you allow the scalars coming from B, and A is actually free module over B, then you have a basis of A, okay, with like that is B basis. Whenever you have relations among some combinations of that basis where scalars you allow to come from B, so if that relation is 0, then you just should show that it's same as like replacing field by this B. Okay. So yeah. So now, yeah, what are we trying to do? Like if you have G being G1 direct sum G2 as a vector space, then like I said, UG1, UG2 both can be embedded inside UG, and then we will identify UG1, UG2 with their respective images. So then you take all possible products from those elements of UG1 and UG2 and then take the span of that. So that is what this, okay. So then that will be exactly UG. So how do you do this? So for example, you take the basis of G1. So let's call it some xi I in I, and then you take basis of G2, which is yj j in j. So then you know that you have basis of G1. So this B, which is the union of Xi, Yj, will be basis of G. So now what you do, you just look at some ordering. Okay, this I you can actually have total order on I union J, and then using that order. So if you take total order on I union J, if you restrict to I and restrict to J, that will be again total order on I and J respectively. So now you fix this total order on this I union J. So now you can write down PBW basis. Okay. So if you write down the PBW basis, so how it will look like. So let's write down this more practical one. You have xi1, etc., xik. You allow I1 less than or equal to etc. Okay. You allow I1 less than or equal to etc. Ik. And then you have yj1, etc., yj L, where again you allow etc. J1. Okay. So now this is going to be basis for your UG. Okay. Okay. So I guess you should actually choose your order correctly. So what you can do, you can actually okay. This is just not a problem. So these elements that comes from this product, okay. So this is going to span UG. Okay. So this actually like
I guess you need to give some powers to the. I mean, you need to.
no, I put the equality, na. To count it with repetition, not a problem. So yeah, writing either xi1 power r1, etc., xi k power rk. So you can go from this to this by just allowing j1, j2, etc., js, where j1 less than or equal to etc. less than js. So this either you write it with strict inequality or with less than or equal to, not a problem.
Yes. Yeah. Thank you.
Yeah. So now you just simply take the PPW basis. Okay. So then you can easily see that these elements will span UG. Okay. So that actually tells you that this equality we have. And now you can repeat this for any k number of subalgebras. Okay. You take G to be G1 direct sum, G2 direct sum, etc. direct sum GK. But then this direct sum is as vector space. So then UG will be just a product of those individual things. So UG1 times etc. UGK. So if you take G equal to G1 direct sum etc. GK. So this has a vector space. So then UG will become UG1 times etc. UGK. Okay. So this is just as like so the way of writing this actually helps a lot in highest weight theory. So maybe like yeah. So when they do highest weight theory, you will see the applications of this. Okay. So let's actually start focusing on proving the PBW theorem. So let's actually focus on this basis thing. Okay. I'll start with the new page. So if you are comfortable, you can just simply take finite basis, not a problem. Okay. So let's fix I and I to be the basis of G. So now I will only use small x size. Okay. I'm going to identify G inside UG and then all the elements of G inside UG. There is no issue. So we fix the basis and then we want to claim that we have this PBW type basis. Okay, so claim is this xi1, etc., xik, where I1, etc., ik comes from I, such that I1 less than or equal to, etc., less than or equal to ik. So this form a basis for UG. So now this actually kind of simplifies our notation. With the repetition, you can just don't need to mention the exponents. Now when k equal to 0, this is just empty product. You take 1, okay? Because that 1 corresponds to that 0th degree space, which is complex numbers. When k equal to 1, you have this xi, ini, which corresponds to 0. Okay, so these things should be noted. And k equal to 0, it's an empty product. It corresponds to 1. So this is empty product. When k equal to 1, you get xi, ini. So this is the basis of. So likewise, you will be actually having things. Okay, so now how to actually go about it? So there are two statements here. We want to prove its basis. So to prove basis, we have to say it spans and then it is linearly independent. So spanning is actually somewhat easier. So that is what I was trying to say yesterday. But linear independent actually involves bit more. Okay. So let's see how to prove spans. So you need to actually first see that you have a natural spanning set. From that, you start cutting down and then reach here. Okay, so there is this natural surjective map from TG to G. And you know that you already have a spanning set for TG. And then if you take the spanning set means basis of TG and then take image of that, that will be spanning set for UG. So if you just take elements of this form, xi1, etc., xik, where I1, etc., ik comes from I. So there is no ordering in on this I1, etc., ik. You allow them to be anything. So then this definitely spans UG. Because this spanning set is indeed comes from basis of TG. So image of that is this spanning set. Okay, so now from this, somehow you need to go to ordered monomials. Okay, let's see how one can do this. So, like I said, so you induct on the length as well as the number of switches that you are actually going to do in this word. Okay, so it's better to think them as words. So you have xi1, etc., xik. So if they are in the correct order, then there is nothing to prove. Okay, you just already there in the correct order. So now what we do? So we are going to induct on this k and as well as the number of switches needed to write this permutation. Write this permutation in the increasing order. Okay. So is that clear what I'm talking about here? For example, like let's take something like this: 3, 2, 1, 1, 4. Okay. So this is not in the correct order. Okay. But what you want to do, you want to actually kind of bring it to the correct order. So the correct order will be, okay, the finally you will reach 1, 1, 2, 3, 4. But then there will be some intermediate steps. And if you think about it, to reach to the correct order, you will be only actually kind of doing this very basic switchings. Okay. So adjacent positions you need to switch at a time, so that successfully you switch, then you will be reaching this. For example, you scan it from left to right. So then first you do like this. You switch these two. Okay. So you switch 2, 3, 1, 1, 4. And then from here, so this is again you switch. So 2, 3, 1, 3, 1, 4. So every time what I'm doing, I'm reading from left to right. And then I'm seeing where the switch needed. Okay. The very first instance where the switch is needed, I'm just swapping them. Okay. So like this, I just go. So 2, 1 will be switched. And then from here I'm doing. So you can see that by doing this enough number of times, you will reach to the correct order. Okay. So that is this number of switches that you are required that I'm actually inducting on. So now with that, you can see that. So you begin with this word xi1, etc., xik. If it is already of the form I1 listener equal to etc. listener equal to k, then we are done. So we don't need to do anything. So if it is not in the correct order, okay, let's start with xi1, etc., xik. So if it is not in the correct order, I'm started reading it from left to right. So then very first place where it is actually not in the correct order, I will see that. So that is exactly, let's say, happening at the rth place. So xi1, etc., xir, xir plus 1, etc., xik. So only here it is first instance, it's not in the correct switch. Okay. So then what you do, you just swap them. So, but if you are actually swapping them, then what will happen? So you need to actually we read this xi1, etc., xir plus 1, xir, etc., xik. But then you will be paying some cost by swapping it. So that will be just the commutator xi1, etc., xir, xir plus 1, the commutator, etc., xik. So this is how what will happen. So you have swapped and then you have replaced that by the commutator. But then note that, so this will have actually less number of switches than this one that you started. And then this will have length less. Okay, the length will be less. And then here the switches will be less. So now you can see that by induction, you can write this, this as combination of right ordered monomial elements. This as combination of right ordered monomial elements. Okay, so that actually completes that these elements that you see here in this PBW basis. So that actually spans our UG. So this is also like immediate from that natural map that we defined. Okay, so I guess I called it omega. So you have this omega from SG to grade UG. Okay. So since you have this natural basis in SG, which is like this all increasing monomials. Okay. So then the image of that will be spanning set in the grade UG. like I said, grade UG is isomorphic to UG, so you are not going to lose anything. So you just go there to UG, then you will get this set, and that will be spanning set. So it's already embedded in this map omega. Okay, so that's the easy part. But now, what you want to do? You want to actually prove this is indeed linearly independent. Okay. So to do that, so you need to actually uh, so whatever Humphreys actually does, it's more representation theoretic proof. Okay. But actually, Carter just takes out a core part of that proof and then just writes it down here. Okay. So, so what he says actually, like if you have this basis, then naturally this UG is isomorphic to SG as vector space. Okay, so that means you already so there is this natural vector space isomorphism that you have from SG to UG. So that is something you need to establish. Okay, but if you're looking for something like that, then first you define a map from the tensor algebra to UG, and then you see how much like if you can go modulo the kernel that actually defines SG, then you will be in business. Okay, so then what Carter does, Carter's idea, okay, define this linear map. So let's call it theta from TG to UG, such that the kernel of theta contains the ideal I. Okay, this is a two-sided ideal generated by x tensor y minus y tensor x, where xy comes from G. Okay, so and obviously this is a surjective map. Okay, so then you will be having actually induced map from SG to this UG. So then you need to check that actually. Okay, this map. Okay, this map is not just some random map. This must satisfy some condition. So, so then you will be getting map from this TG to SG to UG. So then that will give you explicit linear isomorphism. Okay, so that is what actually Carter does. He is establishing that linear isomorphism very explicitly. But Humphrey's idea is much more interesting, which is more representation theoretic actually. Humphrey's idea. So Humphreys actually just takes this proof from Bourbaki. So which actually says, so you make this UG to act on this SG. Okay, so basically like to make UG to act, you can actually make G to act. So you define this representation. So you define a representation of okay. Okay, so let's write it as a map. So you define this row from G to GL of SG. Okay, satisfying some conditions. So then using that, you can actually immediately see that so you have so you define this representation from G to GL of SG. Then using this, you just prove this elements of this UG indeed linearly independent. Okay, so what will happen? Okay, so basically in this idea, so let me just tell you like So yeah, representation of G will correspond to representation of UG. So from this row, you can go to row tilde, maybe you can call it row itself, from UG to GL of SG. So then what you do, you take this PBDW type basis, okay, that you are interested in. So suppose if you have some linear relations there, so then look at how it acts on SG. Okay, maybe you can actually just apply it on one vector, and then you can see that that action actually gives you some contradiction. Okay, let's do this in much generality, and then it will become clear. Okay, so what do you want to do? So this is the core idea. So you have G, okay, and then you have UG. So you want to show some elements, okay, of UG are linearly independent. Okay, so let's call them like some X alpha, alpha in lambda. Okay, because these ideas will be repeated again and again in representation theory. That's why I'm just formulating it in much generality. So some elements that will comes from this UG, you want to show them to be linearly independent. Then what you do, you construct very large representation. Construct a large representation. Let's call it V, okay, of UG. So that means you have a map from UG. So constructing representation of UG is same as constructing representation of G. So you have a map from UG to GL of V. Okay. So now look at, okay, of course, this is not some random representation. This is some particular representation. And then you have some very specific vector in V. Okay. So most of the time, this vector will be called vacuum vector. Okay. And in this generality, mostly this one will be good enough. So one is in SG is what your vacuum vector. So you have this vector V naught in V. And then what you do, you take all these elements that you are interested in showing linearly independent, and then look at its action on this vector V naught. So now this is subset of V. Okay. So look at X alpha V naught, where alpha in capital lambda. So all possible images of V naught under this X alpha. That's what I'm telling. So you look at this. So suppose if you know this is linearly independent, okay, so then that implies that X alpha is linearly independent. Because,
Sir,
sorry,
sir, what is V here?
so V is that representation.
Oh,
You construct a representation of UG, call it V, okay, and then you have this special vector called vacuum vector. And it is choice only, okay, we are giving some name because this is all motivated from physics. So you have some vector, and then look at the image of this V naught under this all X alpha. So that will be subset of V. Suppose if you know that this is linearly independent, then that would imply immediately that X alpha is linearly independent. So that is just because suppose summation C alpha X alpha is 0 inside UG, then the same thing should give relation here. Summation C alpha X alpha V naught is 0 inside V. Okay, by making it act on this capital V. But here it is linearly independent, so that would imply that all C alphas are also. Okay, so that is why it's important to actually construct this large representation. It's a very core idea that Humphreys actually demonstrate. So, but it is not always easy
I have a
to.
question.
Yeah.
What do you mean by large representation?
Not like infinite dimensional representation, because you are looking at UG, na? UG is already infinite dimensional algebra, na?
Yes.
So, and the set that you will be considering is could be large set, okay? and you want that set to be linearly independent, and you are expecting this set to be linearly independent, okay? The images of V naught under the X alpha. So you expect that it should have same cardinality as lambda. Huh? So your space should be as big as this. Otherwise, you will be not having. Sorry, 1 minute. Okay, any other question? Shall I continue?
Sir, how did we find or construct this vacuum vector?
No. I'm saying like, so this is just a very general idea. And depending upon situation and all, you will be actually, there will be a natural choice. Okay, for example, if you take Humphrey's proof of this PVW theorem, okay, he constructs this representation. So naturally, G acts on SG. Okay, you have a this representation rho from G to SL, GL of S, GL of SG. Okay, so then the vacuum vector will be here 1, that is in SG. So mostly that some basic vector that you are actually considering. Okay, so there will be a natural choice in the representation that you construct. So I'm giving, this is very general picture. Okay, this is what you do most of the time in representation theory to prove something is linearly independent. That is actually part of your algebra. So you have an algebra and you want some of the elements to be linearly independent. So then you construct some representation and make those elements to act on that, and then you apply it on very particular vector and then see what will be the images of that. And then if that is linearly independent, then you can say that the vector that you started with will be linear. Okay, and this is something, it's not that you do only for algebra, you can also do it for the representation itself. Then you will be actually constructing some other space on which the representation will act. Okay, representation space will act. Okay, this is like getting into what is called notion of vertex algebras also. Okay, so yeah, I don't think I will have time to go through the Humphrey's proof, but anyway, but the technicalities that you see in Humphrey's proof, that constructing very specific maps and so on, just he is doing it because of this, nothing else. Okay, if you write down explicitly what is the meaning of this G acting on GL of SG, and you expect it to act naturally, na? You take Xi, and Xi should act on the basis of SG via left multiplication. Okay, that is what you expect, but it is not quite left multiplication. You have to go modulo something. Okay, that is why uh, lots of these restrictions are there. But if you write down what this means, okay, G acting on GL of SG, and then you will see that those conditions that are listed in Humphreys will be very, very clear. Okay. So the notes that I have sent that has this. So let me just show you those relations. Okay, I'm not going to prove. Sorry, anyone has that file that I sent and more notes?
Yeah, you do you want me to share them?
Yeah, that will be.
Just hold on. Ritesh, do you have it?
Yes, sir, I have.
Can you share?
Just a minute, sir.
I got it. Yeah.
Shall I share, sir, or you are sharing?
I'm sharing 1 minute. Yeah. No problem.
Okay, okay.
Yeah. Do you see?
Yes, sir, we can see.
Yeah. So yeah, she actually follows Humphrey's proof. Actually, she has some typos. Yeah, you should be careful in that. Yeah, you can see that you are demanding some map here. Okay. Yeah. So the idea of the proof actually constructing this representation from G to GL of SG. Okay, such as like you take the element xj, that is the basis of this G, and when z is in the increasing monomial, okay, then you just simply multiply by left by zj, okay, and then if it is not, yeah, okay, this j should be just if it is less than or equal to I bar, and this I bar is already written in the increasing order. I1 less than or equal to etc. IM. Whenever j is less than or equal to I1, then you multiply by zj. Otherwise, what will happen? Like you just again multiply, but modulo this Sm. Sm is that up to nth degree. Okay. So then once you construct this, then it is clear that you just apply your PBW basis on this one. Then you will see that you will have actually linearly independent set, because by this construction it actually clear. Okay, so this xj you are multiplying by zi bar, so you are getting zj zi bar, which is still j is less than or equal to I bar. It is still in the increasing monomial. So the increasing monomial in the PBW basis, when you apply it on 1 in SG, you will get increasing monomial in the in the space which is SG, and that is linearly independent. That you know, from that it follows that the PBW basis is indeed linearly independent in your UG. Okay, so that's the idea. So this technicalities, okay, that constructing this AB will come down to like constructing some maps from this G tensor SMPS. Okay, and it's just rewriting everything in terms of that. Okay, so that's what this AM, BM, CM. So once you know this such a map exists, then that will give you that this map that actually satisfying these two conditions. Okay, so this is just simply technical, nothing else. You should sit and just work it out. So again, you can do it by induction. Okay, constructing this, there is no issue. So again, Carter proof is almost similar only. It's not something different. But what happens like on the nose, you are directly defining map from SG to UG, which is a linear map, and that is an isomorphism. Okay, instead of going through like this. In some sense, the map that you are defining from UG to this HG you take elements of UG, apply it on that vacuum vector. So that is the map you are actually defining from UG to SG. So maybe let me write it down, so then it becomes clear. Okay, so suppose if you have constructed this representation, let's say, then from this you have this natural map, okay, from rho tilde from UG to GL of SG. So now what do? You take down this rho tilde 1 bar. So this is a map you are defining now. So this is representation. So now I have chosen this vacuum vector 1 in SG. So now what I'm going to do, this rho tilde 1 bar is a map from UG to SG, which takes X2 just X applied on 1. Okay, you take this vacuum vector to be 1 and then you take X and then apply X on 1. So this is nothing but rho tilde of X applied on 1. Okay, and this is the map that Carter defines. Okay, so this is the map Humphreys defines. Okay, so we will directly define this instead of Humphreys. Okay, so let's see. Okay, I have. Okay, I have like less time, but again, the checking we can do it during the tutorial, not a problem. Okay, so how do you construct this map? Again, you use induction to construct this map. So you write down what is required, then it will be applied. Okay, so here is the map. So we want a map from theta to TG to UG. Okay, so what I said earlier, you need to take the inverse. Okay, not. So here, this is the isomorphism in some sense, but you need to take the inverse of this. So you have the map theta from TG to UG, satisfying the following conditions. Satisfying. You take theta of, let's call it xi1, tensor, etc., tensor xik. So this is the standard basis of this T. You send it to, okay, sorry, I guess you define it UG only. Sorry, SG. So you define a map from TG to SG, not the other way. You take this xi1, etc., xik, that element, and that is mapped to its image, which is, let's call it, I guess I called it, maybe let's use zi1, etc., zik. So what I mean by that, the image of xi, we are calling it zi inside SG. Okay. So if this is in the correct order, so the image of the monomial is exactly zi1, etc., zik if it is in the correct order. So when it is not in the correct order, you need to worry. Okay. Again, you want to go modulo now the ideal of UG. So that means x tensor y minus y tensor x minus xy. So that means whenever it is not in the correct order, so let's say I1, etc., tensor I R, tensor x IR plus 1, tensor, etc., tensor x I K. Okay. And then, so it doesn't matter like what element that you are taking. So whenever you want to switch, so that is where this relation will be used. So whenever you take this R plus 1 place, whenever you want to switch, you have to pay the cost. So the image of this, so you are switching it here. This should be exactly because you want to go modulo the kernel. So when you switch, the image of theta of this difference should be theta of xi1 tensor etc tensor the bracket xir plus 1. Okay, tensor xik, and this should be true for all I1 etc in, sorry, ik, and then all are strictly less than. So now there is no restriction on the indices. Okay, you just you want to do it for all possible indices. So if you do this, you know already that this will form a basis for TG, and naturally the kernel of this will have the ideal of that defines UG. Then you can actually define a map from UG to SG, and that map actually does the purpose. Okay, so how do you go about it? You have to use again induction. Again, induction on the length as well as the number of switches that you make. Okay. So let's start with induction. So now what you do, like you need to define. So this t power, let's call it n. So this is this n degree polynomial. Okay. So this is the polynomial xi1 tensor etc tensor xin. So span of this. So let's stop actually denoting it as Tn of G. So let's use this Tn. So then you can see that it may not be in the correct order, but then you can look at this number of switches that you are actually doing. So that is, you can actually take this number of pairs R, S such that this I R is not in the correct order. So R is less than or equal to S, but then IR is greater than IS. So that is the only thing that you need to worry. So this is the switches that you are actually defining. So for each monomial, you can associate this number, and we are going to actually induct on the length of the degree of the monomial as well as this number. Okay, and assume that you have defined the map up to actually n-1 degree. So then you want to define it for n degree polynomial. Then you want to actually induct on this number of switches. Let's say you have defined it up to some ith switch. Okay, you can define this Tn comma I to be the span of all these monomials. Okay, such that the length is when the degree is n, and this number. Okay, let's call this as switch number. So this is actually exactly I. Okay, so then you can see that this actually forms filtration. So you can actually take it to be utmost I so that you will get the filtration. So the number of switches is utmost I, so that this is actually giving you the filtration Tn0, Tn1, and so on Tn. Okay. And if you have defined it for Tni, then you want to go to Tni plus 1. Tn0, it's easy to define. Because Tn0 is nothing but there is no switch. Okay, so note that Tn0 corresponds to I1 less than or equal to In. So for which you already have the definition. So theta of xi1 tensor etc xin is defined to be zi1 etc zin. So assume you defined it for up to Tni. So we need to define it for Tni plus 1. Okay, so if you take this element xi1 tensor etc. that has I+1 switches. Okay, switches to be I+1, and the length again degree is n. So what will happen? You have like you can choose the very first switching where it is happening. So it's the same idea. Okay, so you see where first switch is happening. So you demand that, okay, the formula actually tells that theta of this should be equal to theta of xi1 tensor etc xir+1 tensor xir tensor etc tensor xin plus the theta of xi1 tensor etc xi bracket r+1 tensor etc tensor xin. So now note that, okay, so this is in a way demanded in the definition of theta. Okay, so if you actually if you want theta to satisfy your condition, this is something demanded. So now what you can do, you can choose R, the place where the correct order is not there. So then by definition of theta, you demand that this is same as this plus this. So then you define it to be this. So now if you read this word, this will have less number of switches. It's a length n, but less number of switches. So by induction, so this is there inside Tni. Okay, this is there in Tni+1. So by induction, this is defined. Similarly, this one, if you take, this is there in Tn-1, whatever j. Okay, so by induction, this has length, the degree is smaller. So this is also defined. So both are defined. Okay, so that way you can define theta, no issue. But this has some well-defined problem because you are actually started with degree n element and then gone down to something smaller. Okay, so you started with xi1. Okay, let's drop that tensor. Okay, xir+1 xin. From here, you have gone to xi1 etc. xir+1 xir xin plus xi1 etc. the bracket or r+1 xin. So you were reading like from left to right, the very first instance that you are actually choosing this, you can take that and then you can define this. But then if you do that, then you need to verify, okay, really that, so the well-defined won't be a problem. But there could be lots of relations that are happening in UG. Then you will be in getting into some trouble. Okay, so instead of that, what Carter does actually, so you do this without first making any choice of R. Okay, you choose some R where it is not in the correct order. So you choose some rth place where it is not in the correct order. Then by demanding, theta is defined that way. Okay, but then it actually leads to this well-defined question because this R is not necessarily unique. So you may actually have some other position for which the swipe can happen. Okay, it may not be in the correct order. So then you have to prove this well-definedness. That is the only thing that needs to be checked. Okay, the well-definedness. So what in case if you switch another position like yes to position where the switching can be done? So then you have to say that it doesn't matter whatever the position that you choose, independent of that, what is on the right side should be equal. Okay, so then that actually gives you the well-definedness. So then that would actually define the map. So once you have defined the map, so then it is clear that, so you can go back to the definition and see. So this condition tells you the kernel of theta will contain the ideal that defines UG. So that means this is actually going to define map from UG to SG. Now, if you take this PBW type basis and then look at the images of these words that comes from PBW basis, that will be mapped to these basis elements of SG from the construction. So that means because the image is linearly independent, so the original set must be linearly independent. So that is how you actually prove this PBW theorem. Okay, so I will stop here because we are running out of time. So this well-definedness we will check during the tutorial. Okay, so yeah, thanks.
Yes, shall we start? Stop recording, sir.
Yes. Any quick questions?
Can you repeat the last part? Part beyond the well-definedness.
See, the thing is, we are making a choice to define this theta. So let's say I want to define theta of this, which is a degree n monomial you want to define. So by induction, you know that the theta is defined up to degree n minus 1 and the number of switches up to I. And you are assuming that this is in Tn I plus 1. So it's a degree n which has I plus 1 switches. So somehow you need to go down. Okay. But what is happening when you swipe, okay, when you switch this IR and IR plus 1, then this element is in Tni, which has degree n and the number of switches will be at most I. And here, if you see, so this is there in Tn minus 1. The degree of this will become at most n minus 1. So that means theta of this is defined. Again, theta of this is defined by induction. So you define theta of this part to be just equal to, so you define to be this, you define this to be just sum of these things, because that is what your formula says. You are demanding that the definition of this is sum of these two. But the problem with this definition, the choice of R, the R that you have chosen is actually you are choosing any place for which the switch happens. So you can also come up with another yes to position where switch can happen. So then you have to say this definition is independent of the place that you switch. Okay. If you allow another switch, again, the images should be equal. So then that actually will tell you that it's only depending upon the monomial that you started with, not the position that you actually chosen. So that will define the spot you need to verify. That will actually follow from Jacobi identity.
Okay, sir. Thank you.